morning, my YouTube viewers. It is Crystal here, and what we're going to discuss in this video is another technique of experimental design, and we're going to cover a model of factorial design. So factorial design tests multiple factors simultaneously by creating combinations of all factor levels. It is ideal for exploring interactions between factors such as the effect of fertilizer type and irrigation frequency in agriculture. So what we're going to do is we're going to simulate some data to demonstrate factorial design. So the example we're going to have is we're going to analyze fertilizer A and water level B on plant growth. So plant growth is your dependent variable, which is Y, and fertilizer and water level are going to be your independent variables, being X. So the null hypothesis is there's going to be no significant difference, and the alternate hypothesis is going to be there is going to be a significant difference. So we're going to simulate a 2x2 factorial design simulation. So the first thing that we want to do is we want to set our seed. And the reason why you set your seed is so every time you run the program, the variables are going to be initialized to the same value. So you type set.seed brackets 1, 2, 3, and you can put any number you want within the brackets. And now what we're going to do is we're going to set our factors. So fert becomes factor and a vector and a repetition vector with a vector in it of F1, F2. Those are your two units within the vector, and each is 40. So that means there's going to be 40 F1s and 40 F2s. So you're going to have 80 altogether. And water is going to be a factor. It's going to be a repetition vector and another repetition vector with high and low in it. And each is 20. And you're going to do that 2 times. So 20 times 2, there's going to be 20 lows and 20 highs. And you multiply that by 2 to give you 80. So you're going to have 20 low, 20 high, 20 low, 20 high. And so the water is going to be 80 elements as well. And then we're going to calculate our true effects. So fert effect becomes a vector where F1 is 15 and F2 is 18. So you can see already that F1 and F2 have different numbers in them, and I'm going to take it as a mean. And then the water effect becomes a vector of low equals 0 and high equals 3. So we're going to do an interaction. So F2 responds more strongly to high water. So interaction effect becomes if else, brackets, fert equals F2 and water equals high. It's going to be a 2, otherwise it's 0. So now we're going to simulate the growth. So growth becomes fert effect, brackets fert plus water effect, brackets water plus interaction effect plus R norm. That's a randomly sampled normal distribution of 80 samples with a standard deviation of 2. And then we're going to take all this data and we're going to convert it into a data frame. So dat becomes data.frame, brackets fert, water, growth. And then we're going to print off the head of the data, which is going to be the first 6 columns. So this is the head of the data. So So you've got your data frame, the first 6 rows being your FERT, your water, and your growth. And so this is all F1 because it's going to be F1 for the first 40. And then F2, and then your growth. No, sorry. Yeah, then your water is going to be low for 20, then high for 20, then low for 20, then high for 20. So with F1, you're going to have 20 lows and 20 highs. And with F2, you're going to have 20 lows and 20 highs. And then if you want to, and then this growth, I'm going to take that to be the mean. And then, but if you want to, you can also print the last 6. So you can hit TAIL. And then what that will do is that will print the last 6 rows of the data frame as well. So you're going to have 80 rows. I'm just letting it print off. I'm just letting it run at the moment. So in addition to looking at the head, we're also going to look at the tail. So you've got the head being the first 6 and the tail being the last 6. So you can see that the tail is the last 6 rows of the data frame, which is F2. And then your growth, I'm going to take it as a mean. So now what we're going to do is we're going to run an ANOVA, and ANOVA stands for Analysis of Variance. And in our programming language, you have 2 types of ANOVAs. One ANOVA is when you use it for hypothesis testing, and then the other type of ANOVA is when you use it for linear regression. So we're using the ANOVA that is used in linear regression. So fit becomes AOV brackets growth, which is your dependent variable being y, tilde, FERT, and water. And FERT and water are your independent variables being x, and data equals data. So we're going to summarize the fit. So we're going to come down here. So you've got FERT, water, FERT colon water, and residuals. So your degree of freedom for FERT is 1 because you've got 2 types of fertilizer, F1 and F2. So you calculate your degree of freedom by subtracting 1 from that. So 2 minus 1 is 1. For water, it's exactly the same thing. You've got high and low. So your degree of freedom is 1. And then FERT water is 1. And your residuals is, so you've got 2 FERTs, 2 waters, which makes it 4. And then you've got 80 elements total. So 80 minus 4 is 76. So those are your residuals. So you also get your sum of squares, your mean square, your F value, and your P value. So on the FERT, it's a really low value, 3.32 to the negative 14th. And then for the water, it's a really low value, 1.53 to the negative 7th. And then for FERT water, it's 0.0236. So all 3 of those P values are a really low value, being less than the significance level of 0.05. And so that means that you're going to have to go with you're going to have to reject the null hypothesis in favor of the alternate hypothesis, which means you're going to say there is a significant difference between fart or water, and in this case, fart and water. So your p-value is supposed to be between it's supposed to be around 0.05. Your significance level is supposed to be between 0.05, but it can go as high as 0.1 and as low as 0.01. And they haven't really set a p-value in this particular exercise, so we're just going to go with the 0.05. Or they haven't really set a significance level in this particular example, so we're going to go with 0.05. So what that's telling you is that they're going to have to reject the null hypothesis in favor of the alternate hypothesis. And then if you see, like whenever we created our sample data, F1 was 15, I'm going to take that as a mean, and F2 was 18, and I'm going to take that as a mean. And then water effect, low is 0, high is 3. So you can see that when we created our sample data, there is a difference. We created it to have a difference between the fart and growth, significant difference between the fart and growth. So it was created to have a low p-value. So now we're going to plot it. We're going to create an interaction plot. So interaction.plot brackets x.factor equals water, comma, trace.factor equals fart, comma, response equals growth. And then color is a vector of steel blue and tomato. Line width is 2. Main is your title, being interaction plot, fertilizer times watering. X lab is the label of your x-axis, which is watering level, and Y lab is the label on the y-axis, being mean growth. So now we're going to print the main effects plot. PAR brackets MF row equals a vector of 1 and 2 fertilizer effect. We're going to plot that. Plot brackets T apply brackets growth, comma, fart, comma, mean. Type is B. PCH, which is your the size of the dot, is 19. Color equals steel blue. Main is the title on the chart. It's main effect fertilizer. X lab is the label on the x-axis, being fertilizer. Y lab is the label on the y-axis, which is mean growth. And XAXT is N. And so then we've got the axis brackets 1, comma, at equals 1 to 2, comma, labels equals levels brackets fart. Then we're going to calculate water effect on this chart. So plot brackets T apply brackets growth, comma, water, comma, mean. Type equals B. PCH equals 19. Color equals tomato. Main is your title, being main effect watering. X lab is the label on the x-axis, is watering label. Y lab is the label on the y-axis, meaning growth. And then XAXT is in. Axis brackets 1, comma, at AT equals 1 to 2, comma, labels equals levels brackets water. And then PAR brackets MFO equals a vector of 1 and 1. So we're going to look at the charts that we have created. So this is your interaction plot. So you can see F1 is the blue dot and F2 is fertilizer. So you can see mean growth and watering level. So, which I find a bit odd because it says with a high watering level, you have a lower mean growth, and with a low watering level, you have a higher mean growth. But I just think this is a simulation, and this is fake data that we're using, simulated data that we're using. So it's a bit odd to me that with a high watering level, you're going to have a low mean growth, and then with a low watering level, you're going to have a high mean growth. But this is just simulated data, because I would think that if you watered your plants more, you would have a better mean growth. But this is just simulated data. It's not real data. And then the next chart we're going to make is going to be the main effects, if I can find it. So you've got your main effect on your fertilizer, and you've got the main effect on watering. So again, you've got for the fertilizer, F1 and F2. So F1 is lower than F2, so that's telling you. And then for the watering level, the high is lower than the low. So again, this is just simulated data that we're using. And then so what I would think that the more you water the plant, provided you don't overwater it, it's gonna grow better. But this is just simulated data for this exercise to show you how we do a factorial experimental design. So that concludes this video. The next video is going to be another topic in experimental design. So I hope that you decide to watch it, and I hope that you got something out of this video. See you next video.